let's make a start.
Hello and welcome to the second in the series of round one preparation run by Dr. Andrew French. So I hope you've had a go at last week's questions and are willing to have a go at this week's. So you're going to see them done fairly quickly, and it's very important that you then follow up by trying them out yourself to develop that skill, that expertise, that sort of working through the sort of the sticky points. So, welcome, Dr. French.
Okay, good evening. Welcome, everybody. Welcome to the Physics Olympiad's round one training. If you are new, very nice to meet you all. And if you came last week, thanks for coming back. Right, so we are working our way through the 2023 paper. So that's going to give you some inspiration of how to solve these round one problems. So for maximum enjoyment, we do recommend downloading our special pack, which is sort of one question per page. It'll look like the sort of thing I'm going to be working on. So you've got something you can check your workings or copy things out and have a discussion later. Where can you get this? That will be put in the Q&A in the chat by my fantastic volunteers from Oxford University. It's also this particular website here. It's called the Eclecticon, and I have a BPhO Physics Olympiad page with all papers going back the last 10 years. So the one question per page workbook is kind of the thing you want to click on and print out. So if you haven't got that, you've just got some paper, that's absolutely fine. But for sort of maximum enjoyment, I would definitely have a go at looking on this. I'll tell you the questions we're likely to do next week as well. Right, okay, so let's, without further ado, I like a lot of hearts and claps. Thank you very much. So yes, this is a semi-interactive session. So if you've got some questions, put those in the chat and our fantastic students will answer them. But you never know. With a bit of patience, I might actually answer them live. So we are going to start off with some basic kinematics, I think. And we're going to start off with part C. So for those who've had a go at this is rather a fun little question. So let's just have a look, and I'm going to do these questions really slowly. I'm going to kind of write down all the things I'd be thinking about. So if you actually want to have a go at round one competitively in a few months' time, preceded by round zero, of course, you'll need to be doing these things a bit quicker. But sort of practice makes perfect. So I think if we can do things slowly and perfectly with as much time as we like, then we can get faster later. I think that's a sort of good mantra. And one of my ex-students actually came to talk to my my current students at Winchester, and he was basically saying, you just got to do lots and lots of these problems, and that's sort of how you get good at it. However, the problems are rather fun. So, and that's even if you don't fancy being a competitive at BPhO, do things slowly and luxuriating the physics is actually a good thing in itself. So that's what we're going to do. So the distance between village A and village B is 50 kilometers. Helen and Robert decide to cycle from A to B. So Robert leaves at 8 a.m. with a certain speed. So we've got some information here. But then he has a break of 30 minutes. Oh, gosh. Right, Helen leaves 30 minutes later and does not have a break and reaches B an hour before Robert. Right. What was Helen's speed? So before we even start, we need to think about what we might draw. So we've got some words which you need to turn to maths, but we need to draw something. Could you put in the chat what you think you should draw? What kind of diagram or graph do you think is going to be helpful here? I'll give you a few minutes, a few seconds to think about that while I take a slurp. Right. What have we got, Kim Lam?
We've got a velocity time graph.
A velocity time graph, an excellent decision. So velocity time graphs are kind of in the middle. You differentiate and you get acceleration, you integrate it, and you get displacement versus time. So a velocity time graph is always a good start. So let's go and draw one. So what we're going to do, if I get a proper pen first, so we'll have, and it's a speed time graph really, because it's sort of a single distance. So I think we'll call this speed. Right, and that's going to be in kilometers an hour. Okay, can I just check, is my screen of an appropriate size to make things clear? Is that looking all right?
Yeah, that looks good.
Okay, yeah.
Fabulous. Right, so let's draw a speed time graph for Robert's and Helen's journey. Right, so 8:30 is here. So let's call that 8 o'clock. Right. Okay. And at 12:40, let's have a look. Well, I suppose we can work that out first, can't we? So let's draw this first, shall we? Oh no, we've got 12 kilometers an hour. So this is Robert's journey. So I'm going to go for Robert. Let's have him as blue. Let's have Helen red. There we go. Right. So Robert's he has a go. So he leaves at this time, and at some point he has a break. That's half an hour. 0.5. We don't know when he's had a break. We know it's just somewhere in his journey. And then he continues till some other time, of which we don't know yet. But what we do know is the total area under that graph, the distance traveled, is going to be 50 kilometers. So let's work it out. So let's put some in, let's just transmit in some slightly better words. So Robert, all right, so he took how long to try? So how many minutes of cycling or hours of cycling? Well, it's going to be 50 kilometers, and he's going at 12 kilometers an hour. And for those of you who might be new to this kind of stuff, putting in the units in the calculation itself is really helpful, because we can see that we've got a distance over a speed, and the kilometers are cancelling. We've got a 1 over hours, which is in hours. So that turns out to be 25 over 6 hours of cycling. All right, plus 0.5 hours of break. All right, and so if you add that up, you get 4.7 hours, or 14 over 3. Okay, so that implies 14 over 3 hours, which is 4.7 roughly. So in other words, if you add that, he's going to arrive at 12:40. So arrives at 12:40. Okay, now whether that's entirely relevant to the end question, it just can actually to give you context. So that's probably the thing I would do first. All right, and so we can also then look at Helen's journey. So she leaves half an hour later. All right, and she's clearly got to go faster than Robert because she doesn't have a break. So she's going to leave here, and her velocity is going to be something like this. We don't know what it is. Let's call that V Helen. And she goes continuously, and then she arrives. We're told she reaches B an hour before Robert. All right, great. So she gets there at 11:40. Okay, so there we go. So that's 11:40. All right, I might call that sort of T there or something like that. Okay, so what do we got? Let's just put some numbers in here on our graph. Let's use a black pen for this. Okay, so what else do we know? So let's put that. So that distance, or that time, should I say, is 0.5. We've now got this sort of time here. So I guess we could work backwards from that, couldn't we? Let's just call that delta T for the moment. And there we are. And we've got 1, which is this one here. All right, so that's nice. So our entire time scale is now mapped out. All right, so 14 over 3 hours is mapped out. So what else do we know? Well, we know the area under Helen's graph has got to be 50 kilometers. All right, so I'm kind of turning the problem. I'm sort of being like a sort of detective here. All right, we know that area there is going to be 50 kilometers. So what are we going to do? So let's sort of like put that all together. So basically, so there we are. Okay, so there we are. So we can sort of say, well, V Helen times delta T must be 50. And what we're trying to find ultimately is Helen's speed. So that's our goal here. So again, all these questions, we're trying to sort of deconstruct them and try and label things as we go. Right, so if we can work out delta T, then we can sort of know it all, really. Well, actually, we can get that from the picture if you think about it. So let's put that. I'll use the black so you can sort of see what's going on. So from the diagrams or the times, what we've got is 14 over 3, which is from 1240 to 0800. All right, so 14 over 3 hours. Let's just put that as 14 over 3. So that's going to be, yeah, so that's going to be 0.5 plus delta T, all right, plus 1. So that means the delta T sort of like, I mean, you could just work it out, couldn't you? 1140 minus 0800 minus a half. It's the same kind of thing. So the key thing is to sort of work out this arrival time. But let's follow it through. So 14/3 minus 1.5, that's going to be delta t, and I make that 19/6. Oops. Okay, that's of course delta t, that's in hours. And then basically I can then put that into this expression here. So therefore V Helen is going to be 50 divided by 19/6. That's in kilometers an hour. And we expect that to be a bit more than 12. And I reckon that's about 16, which is about 15.8 kilometers per hour. So approximately 16 kilometers an hour. Okay, so there we go. So it's the sort of thing that's just not too hard, but you kind of got to sort of deconstruct the question. So I guess if I made life any difficult for myself, I could probably say, you know, the 11:40. So it's arrived at 12:40, work back an hour, and I could sort of go directly to my delta t if I want. But to be honest, it's about sort of clarity, really. I didn't really need to work out my 12:40. I could have just had 0.5 and 1 and a delta t. So in some ways, actually, this bit is just extra. All right, so it might be easier. But we do need to work out 14/3. So that's important. Okay, so there we go. All right. Okay, so in total, what we've done a speed time graph to represent the problem. We've tried to sort of work out some things which we think are obvious. So, for example, how long, you know, what's the total length of time that Robert took? 14/3 hours. So from 8 o'clock to 12:40. And then from there, the principle being the area under the graph is the distance traveled. It doesn't matter, you know, when the break was taken. In fact, that's it's not irrelevant because you need that to work out the total amount of time. But there we go. So there we are. Does anyone have any questions about what we've done before we move on? Am I still there, Kim Lam?
Yep, you're still there.
Marvelous. Right. Okay. So we'll do another little question, which is on classical mechanics. And so we've got a gravity one. So this is rather nice. Let me just find my other mouse. Where's my wrong mouse? There we go. Right. There we go. So turns out there's many things you can do with constant acceleration motion. So let's go and have a little look. An object falls under gravity. The ratio of the distance fallen by the object in the last second of its fall to the distance covered in the last but 1 second is 3:2. And this is kind of reminiscent of how Galileo apparently figured out all this stuff by rolling balls down slopes and sort of recording, you know, when the sort of times when they pass through little gates. So let's draw a picture and then let's see how we get on. So what we're doing, so we've got some sort of ball which we've dropped, and yeah, we're going to. I think as we could sort of think about it, it's starting from rest. I think that's probably a fair assumption. So yes, so what we're gonna sort of, I guess we should say, ignore air resistance. Okay, so look how I'm writing on this. You can write on your papers, everybody, if you do round one. We're going to go for a start from rest. So I'm going to sort of make sure I've got all my assumptions. So let's go and draw it. So I've literally been doing this in my first years today. I got them to. I've got this big. Every physics teacher needs a 2-meter stick. It's the nearest millimeter. There we go. So the ball starts here, and there we go. That's going to be dropped here. And there we go. So there's the floor, something like that. Okay, do we care about the input? Yes, we do. So let's say the speed at which it hits the ground, let's call that V at time t. Let's have that to be distance h. Okay. All right, so there we go. We want to find that. Let's call that h. And there we are. And so basically what we've got, the ball is dropping. Okay, so now we're told, what are we told? So it's the last but 1 second of its fall. So let's have the fall distance to be parameterized, and then we can take 1 and 2 seconds from that. All right. So let's define the fall time to be t seconds. So this is the kind of tricky thing with a lot of these problems, is that you've got something which you want to find out, but it's going to be in terms of something which you don't know, you didn't know you wanted to know, right? So you have to kind of invent something, a parameter in this case. This is the time it takes to fall. Try and work that out, and then hopefully that helps you to solve the problem. And if you can't immediately see what that's going to be, that's not a problem. What you want to try and do is write down relationships that match the question, and that's where the puzzle comes in. So what we can do, I suggest we put some time here. So this is time is t seconds, and then we've got the last but 1. So we want t equals t minus 1, and let's go for t minus 2. All right, so we're kind of hoping that the full distance is a bit more than 2 seconds. Right, so we've got now we've got some sort of some times, if you like. So if we say that t equals t minus 2, the ball gets here. All right, so there we go. All right, so that's t equals 0. So okay, it's going to be moving at some speed there, and then at t equals t minus 1. Okay, so there we are. We might expect this to accelerate, so it's getting a bit further each time, he says. Right, and then we've got our collision, and that's moving at velocity vt. Okay, so let's put some distances here. So let's call x1 to be this distance here, because we've got h already written, and let's call x2 to be that one that matches the 2 seconds we've taken from t. So we've got a kind of hopefully a memorable series of labels. So I think that covers everything that the question talks about. It said the ratio of the distance fallen by the object in the last second of its fall, right? So that's this distance at the end, compared to what it is the last but 1 second is 3 to 2. So what we can do is we can kind of write that stuff down. So let's go and sort of write down some maths first. So firstly, we want to know how far it will fall in t seconds. So if you can get onto the chat, please. If we're dropping a ball from rest, what is x versus t if that is g meters per second squared? Let's take that as 9.8, shall we? What have we got, Kinman?
Half gt squared.
Great, excellent. So yes, so in general, if we fall from rest, we expect our velocity versus time to increase linearly. So v is gt because we've got a constant acceleration motion. So that's our key observation here. So we've got constant acceleration motion. Of g is 9.8. Oops, I go for 9.8 meters per second squared. All right. So if you've got that, the area under that graph, or the integral, if you wish, that's t seconds. All right. Then what we've got is the distance traveled, x, is going to be a half times the base times the height, which is a half gt squared, which is quite nice. But of course, we can integrate it and get the same thing. All right. So we know that x is also the integral of the velocity time graph. But in this case, velocity is linear, so we don't need to use calculus. Right, so let's write that down. Starting from rest. So what have we got? We've got x2 is going to be a half g and big T minus 2 squared. All right. We've got x1 is a half g big T minus 1 squared. And we've also got h equals a half g t squared. 1, 2, and 3. All right, and we can also we want to try and find the final part, but let's do that a bit later. This is part I. Okay, so what do we want to do? We want to find h basically, given this information. Well, let's just see how many unknowns we've got. So we've got t1, x1, and x2. We've got 3 equations. Well, that should be good. That should tell us. That should basically allow us to find that information, right? So, oh, hang on a minute. No, we do need one more. Oh, no, because we've got 3 to 2. So we need one more. We need one more equation to help us to solve this. So it says the ratio of the distance fallen by the object in the last second of its fall. So what's that going to be? So h minus x1 is that. So if I write this in the text so we can be really clear what's happening. Okay, it's for the distance covered in the last but 1 second. So that's going to be x1 minus x2. So x1 minus x2. So there we go. So we've got h minus x1 over x1 minus x2 is 3 over 2. So that's what our last equation is going to be. So now we have basically deconstructed what the blurb tells us, and we've got 4 equations, 4 unknowns. Hooray! So that should at least give us a fair chance of solving that system. So 4 equations, 4 unknowns. All right. So now we should be able to solve it. Okay, so now we're kind of in math land, right? So let's put that all together. Now, let's substitute, I think, equations 1, 2, and 3 into 4. I think that's going to make lots of sense, really. So let's go and do that. So if we have equation 4 here, firstly, do we have any questions before I do this? Because we've kind of reached the end of our physics for the first part of this question now. We're going to go and do some math more. Anyone got any questions in the chat?
I don't see any questions.
Marvelous. Right. So there we go. And I think its point is that we've spent some time, or at least I've spent some time, hopefully you have too, in really making a clear diagram. This could be very confusing otherwise, all right? Particularly, last but one, etc. We've got a nomenclature here, which I think is much more logical. So that statement, I'm going to highlight this. So the ratio, that bit there is what equation 4 is all about. Okay, so let's go and do it. So in 4, let's substitute. So h minus x1. And we'll put 3 as well. So what have we got? I'll use that in red. So we've got a half g big T squared. All right. And I think what we'll do is we'll see if we can find T, because we can substitute for everything else now. So x1, that's a half g T minus 1 all squared. Right, x1, a half g T minus 1 squared. And x2 is a half g T minus 2 all squared. And that is 3 over 2. Oh, this is looking good. So let's get rid of stuff. We can see that half g cancels. Lovely. That's all very nice. Let's expand everything out. So, and I'm going to multiply through with the denominator here. So what have I got? I've got t squared. Let's keep with red. So t squared minus, and I've got t squared minus 2t plus 1. It's my math practice. If I've got a minus and I've got a bracket, I'm just going to deal with that minus sign a bit later, just in case I mess up here. All right, so I'm going to try and do one thing mathematically, which is to expand that bracket. So t squared minus 2t plus 1. Remember, I'm going to take it away. And I've got 3 over 2. And I've got what's downstairs. I've got t minus 1 all squared. So that's going to be t squared minus 2t plus 1. And I've got another minus thing. So let's do the same. So we've got t squared minus 2 squared. So that's going to be minus 4t plus 4. Right. Let's sort all these numbers out. So what have we got? We've got t squared minus t squared. We've got a plus 2t. We've got a minus 1. And then we've got a 3 over 2 here. We've got a t squared minus 2t plus 1 minus t squared plus 4t minus 4. Right, let's sort this all out. So what can we cancel? We can get rid of the t squareds. There's a t squared we can get rid of here. And let's put the 2 on this side. So we've got 4t minus 2. And then we've got a 3. Let's just sort this out first before we do some multiplication. So we've got 4t minus 2t, which is 2t. Oops, that's a bit squiggly. Let's try that again. There we go. And then we've got a plus 1 minus 4, which is minus 3. If I've got this right. Yep. I was just checking my thing I did earlier. So what have we got? We've got 4t minus 2 equals 3 2s of 6, 6t minus 9. Right, so let's put the t's on one side. So that's 2t. And we've got 9 minus 2, which is 7. Hooray! So t is 3.5. Yes, that's what I did last time. Marvelous. Okay. Right, so we've worked out what t is now. And if we know t, we can now find h, and we can now find v. So the problem is solved. This is the hard bit. So we can use, so in which equations? In 3. So we've got h is a half g t squared. So therefore, h is, I think we're going to use 9.81, something like that, or 9.8. So half 9.8 times 3.5 squared. So if you do that, it's about 49 over 8g, which is about 60 meters. And that's in meters. Okay. And then the last thing we want to do is find out the speed at which it hits the ground. Well, that's really easy. So that's a nice sort of like conversion, if you like, to use sort of rugby analogy. So VT is going to be G big T. So therefore, VT is 9.8 times 3.5, and that's meters per second. I make that 34.3. That's quite fast, actually. So maybe air resistance does need to be included. But there we go. All right. So I think that's a really nice question. And it all kind of gets, you get the sort of the final bits very quickly. But it takes a little bit of a while to set it up. So just as a recap, what we did, the key thing here is to draw a diagram to define various quantities, in this case, the displacements that correspond to the times we want. So big T second being the full time, then we can do T minus 1 and T minus 2, and we can have X1 and X2 related to that, okay? So that's really what this question's about, is kind of modeling rather than the maths, although the maths is quite nice as well, okay? And I guess our math tip is to, be quite disciplined with our use of expanding brackets and all that kind of stuff. But there we go. All right. So I hope that was fun. I'm going to might move to something a bit different. So we've done lots of classical mechanics so far. So I think it's time we do something electrical. So I'm going to go to question G if you're doing this manually. So we'll do F next time, and it's one of these, right? So do we have any questions or any queries before I continue?
All looks to be good in the chat.
Amazing. Right. Okay. So we've got the resistance of a copper wire 1 meter long. Right. Okay. Let's label some things. Let's call that L. L1 maybe. All right. With a mass of 1 gram, M1. And it's a resistance. Let's call that R1. All right. Find the length of the wire of the same material. It looks like a key phrase, with a mass of 1,000. So I kind of let's call that. I'm going to call that M2. That's R2. Okay. Right. So if we've got a wire, well, we've got a length and masses and all that kind of stuff. So we've got a resistance and a length. So we need a relationship between resistance and length and something else. So let's go for a wire, conventionally a circular cross section. Let's call that L. And I'm going to hazard to say that. Let's call that A, shall we? A cross-sectional area. So what's the resistance of a wire of cross-section A and length L? You put that into the chat. If you can find a Greek symbol, even better. But tell us what the other quantity is. What's R? Just a quick slurp.
We've got rho L over A.
Excellent. So the resistivity. So rho L over A. So there we are. That's called the resistivity. And that is what the same material means. Okay, not density. All right, it's resistivity. Now, okay, so there we go. And a nice aside, all right, is why that might be. Well, I call this electric sausages, but if you get like a couple of pens which are the same, so if you have a pen which is 1 ohm, and you connect it to another pen, that's 1 ohm, and you connect it to another pen, that's 1 ohm, right? Then that's equivalent. Hopefully, all of you know that that's 3 ohms. Okay, so the idea is we, n pens. Okay, it's n ohms. So R is proportional to length. All right. So the number of electric sausages we have, the longer it is. Now, if we get our electric sausages and they're all 1 ohm still, all right, and then we kind of bunch them up and wire them in parallel like this. Okay, so each one of those, if we put a voltmeter on them, all right, so if I connect that up to a battery, of 1 volt, right? What we've got is we've got 1 amp drawn through each electric sausage, all right, each resistor. Okay, so therefore the total current with 1 amp, 1 volt of EMF, all right, is going to be, so we've got N here, so N in parallel is going to be N amps. Oops, N amps. Okay, so the idea is our overall resistance, so our equivalent resistance, right, is going to be, so V equals IR, so V over I, this is going to be 1 volt divided by N times 1 amp. I'll write it that, so N times 1 amp. Okay, so that's going to be, 1 over N ohms, i.e. 1 over N ohms. So in other words, given the number of resistances scale with the cross-sectional area, so our cross-sectional area is proportional to the number of these, that's the cross-section, is proportional to N. What we conclude, therefore, is that resistance is proportional to 1 over the cross-sectional area. Okay, that's quite a nice thing. So, if you're at the dinner table and conversation gets a bit boring, or maybe turns to politics or something ghastly like that, you say, would you like me to tell you using these, well, maybe you could use sausages, but that might be required to playing with your food. You could use some cutlery or something like this, or some breadsticks, and you could prove why R is rho L over A, and everyone will find you very, very witty and amusing. Okay, so there we go. So let's go from parlour games at dinner to this question. So we've got something which we can use now. And what we just need to do is write those things down. So let's go for it. So what do we got? Let's write this stuff down. So what do we got? So we got R1 is rho, which is our material, L1, and we don't know what A1 is. Okay, and we've got R2 is rho, it's the same material, L2 over A2. Okay, what do we want to find out? We want to find the length of the wire. So we want L2. This is our goal. It's really good to have some algebra articulated clearly as what we want to find out. If you notice, every time I do a question, I'm giving a quantity an algebraic symbol, so that I can relate the symbols algebraically. And most of the time, we want to stay algebraic as long as we can. The previous example of the 3 over 2 is kind of handy for one of the equations. But I'd advise putting numbers in as late as you can. Now, what else do we know? Well, we're given the masses, right? And so there we go. Well, we can do that because we can write down, but we need to be careful here, is that we've got the same symbol for density as the resistivity. So I'm going to call this rho E for electric, okay? And we're going to also have the same rho. That's going to be density. So this is the sneaky part of this question, and I'm sure the person who set this was deliberately being mean to use the question. Two things with the same symbol that are also the same. So resistivity and density. Ha! So make sure we have a separate symbol for them. So what else we got? We've got M1 is going to be the density times the volume. So rho L1 A1. And M2 is going to be the density times L2 A2. All right. So there we go. Now that should be what we've got. Now we don't know if A1 and A2 are the same. So now we've got a slightly harder problem, haven't we? So what do we want to do? We want to find L2. So we've got to kind of cancel all this stuff. Our inputs are L1. Let's just write down our inputs so we know what we're doing. So what are our inputs? Right, what do we got? We've got L1 is 1 meter. So L1 is 1 meter. We've got M1, which is 1 gram. We've got R1, which is 0.15 ohms. We've got M2, which is 1,000 kilograms. And we've got R2, which is 6,000 ohms. Okay, those are our inputs. Right, so we can, anything that's in terms of those things. So what do we not care about? We need to find, so we don't care, about the electrical resistivity. We don't care about the density. We don't care about A1, and we don't care about A2. All we want to find is L2. Okay. It's not that we don't care about these things. It's just that we can cancel that stuff. Right. Okay. So what else should we do? Well, because we've got a commonality, we don't care about rows. They are the same for each thing. We don't need to do it exactly. Let's ratio those two things. Let's give these equations some numbers. 1, 2, 3, and 4. Because now we're in maths land. Okay. Before I proceed, is there anything about the setup that anyone has any questions about? And am I still recording?
Yep.
All good?
I don't see any questions.
Fabulous. Right. So what I just do, well, I think these equations show that we should take some ratios. All right. And R2 is bigger than R1. So let's go for 2 over 1. All right. So that's going to be R2 over R1. The electrical resistances are going to cancel. And then we've got L2 over L1. And then we've got, well, it's the A2's downstairs. So we've got A1 over A2. Okay. Let's do the other one as well. So we have 4 over 3, because M2 is going to have to, it's clearly bigger than M1. So if we go for 4 divided by equation 3. Right, what do we got? We've got M2 over M1. The rows cancel. We've got L2, A2 over L1, A1. Right, okie dokie. So what we want to try and do then is basically get rid of one of those things. So we don't care about A1 and A2. So if we flip those things upside down, so if we basically, if we sort of multiply that out, if you like, and reciprocate, if I use the red equation here, so I can go like this. So if I say that, so you want A1 over A2, so it's M1 over M2 is L1 A1 over L2 A2. And then what we can say, if we multiply both sides by L2 over L1, so L2 M1 over L1 M2 is A1 over A2. That's the ratio that we kind of want here. All right, so I'm looking at kind of both. This is where you want to write them side by side. How can I get rid of stuff efficient? So I'm just going to double check I've got that right. So I think that's okay. So M2 over M1, we flip that upside down. Yep, I think that's all good. So now we can substitute. So therefore, let's change color. So, okay, so therefore, we've got R2 over R1 equals L2 over L1. And it's the A1 over A2, which we can get from here. Okay, which is now multiplied by L2 M1 over L1 M2. Oh, look, that looks quite nice. So we've got, therefore, R2 over R1 is L2 over L1 squared, M1 over M2. We're nearly there. So L2 over L1, that's going to be M2 over M1, R2 over R1, and then we're going to square root that. Isn't that lovely? So that's our maths done. It's in terms of ratios as well, so that's fabulous. So therefore, because L1 is 1 meter, that's all right. So L2 is going to be equal to 1 meter times this square root ratio. So M2 is 1,000. M1 was 1 gram. Haha. So 0.001. All right. And then R2 is going to be 6,000. And R1 was 0.15. Okay. So I make that 200 kilometers. Kilometers. There we go. So we've got quite a long wire here. And then we can then use that to work out, if we really care, what A1 over A2 is, or rather A2 over A1. So now we can find, so A2 over A1 is going to be L1 M2 over L2 M1. So what is that? We can have L1 was 1 meter, so that's 1 over 200 times 10 to the 3. Right, M2 is 1,000. and M1 was 1,000ths. Okay, so what does that give us? That gives us 10 to the 3, another 3, okay, 200 times 10 to the 3. All right, so we've got the 3's cancel. We've got 1,000 over 200, which is 5. There you go. Marvellous. A little bit of mental arithmetic there. So we don't know what A1 is. I don't think we do. No, because we're not given the densities or the electrical resistivity. So we can't go any further, but we do know what the ratio of the cross-sectional areas is. So that could be an extra, but that's not given. Okay, so a question which looks really simple, but actually is a little bit trickier. And again, what's the solution? Is to write down these equations here for what we know in terms of the various unknowns. And it's very common in BPhO for having multiple variants of the same type of thing. In this case, lengths or cross-sectional areas. In fact, the cross-sectional area is like the hidden variable here, or the resistances. So if your habit, I'd really encourage you to do what I've been doing here, is as soon as you see something, label it. All right, and don't call the same thing the same letter. Use some suffixes. All right. Okay, so there we go. I think that's rather cool. Right, so we've got some I think I would probably call it a day for the 2023 stuff, because of course, just doing 2023, you think, well, hang on a minute, I could probably look at this myself. Why am I on this call? Surely I'd want to get some extras. So I'm going to give you a few little extras. So last week we started our 42 project. Which of course is the answer to the ultimate question. So I have a little talk which is about 42, and here is part of it. So this is 42 for today, and let's just see if I can full screen. Is this coming at full screen okay, guys?
Yeah, that looks fine.
Wonderful. So okay, so this is all about electrostatics and also gravity. So if we have a charge, like let's call it some positive charges here, or we could have 2 electrons if we want. I think I've used electrons in my example, but these could be, you could do protons as well. But let's use electrons. I've just realized that my diagram is a positive charge. Never mind, I've recycled it. So if we have 2 positive charges, the electric field that's manifested by my positive charge radiates outwards like this. And another charge of charge little q, a distance r from it, will feel a force of repulsion. What is that force? Well, it's given by Coulomb's law. And this is just like gravity. And we might meet a bit of gravity in a moment. And it's proportional to the product of the charges, little q and big Q, divided by the square of the distance between them. It's an inverse square law. And there's a constant in front. And that's called Coulomb's constant. And it will turn out, and if you're new to this kind of stuff, there's some more seem mysterious, but there's this thing called epsilon naught, the permittivity of free space. And it has a very small number, which means Coulomb's constant, 1 over that, divided by 4 pi, is a very large number. Okay, so I'll give you a hint, the electrical forces are very powerful, whereas the equivalent for gravity is dinky. So this is what the gravitational attraction would be between these two things. Now I'm using electron rather than a proton, okay? So you'll see why in a minute. But it's the same kind of idea. So for gravity, the force between 2 masses, right, is the product of their masses divided by the square of the distance between them. So gravitational attraction and electrostatic repulsion, or indeed attraction, have the same inverse square law. So let's be playful about this. Let's look at the ratio between the electrical repulsion of 2 electrons and the gravitational attraction of 2 electrons, not protons, as I might have indicated here. So if we do that, Fe over Fg, of course, the R's cancel because they both have the same inverse square. It doesn't matter how far away they are. So what have we got on top? We've got the charge on the electron, because that's 2 electrons. We've got this 4 pi epsilon naught. And then downstairs, we've got the strength of gravity. And this is the universal gravitational constant, which is a very tiny number. It's really hard to measure, actually. I've managed to achieve it to 1 significant figure, which I did in the lab using something called the Cavendish experiment. And we spent all day letting a laser sweep across the wall. Use something called a torsional pendulum. It's great. Anyway, if you put all these numbers together, you get 4.2 times 10 to the 42. So there we go. Okay, it's not 42 twice, but if you can kind of neglect the decimal point, it's nearly there. There we are. So that's our 42 puzzle for the day. And we'll finish off with a frankly strange project, which I did today with mine. So if I've got any of my top years, You can give us a thumbs up today. Hello. So we had a bit of a cheese dream today. So we are looking at a problem about a cheese moon. So this is a gravitational problem, and we'll do this now. So there we go. So this is going to be a bit of an extra. I would add this one to my little notes here. Right. So we've got the cheese moon problem. So here is the setup. So obviously in kind of mythology, you talk about the moon made of cheese, and of course that leads to quite a good joke. Of course, that what happens if a cheese moon is hit by an asteroid? Anyone know the punchline to this one? Well, okay, I think that's an appropriate pause. Well, it leaves plenty of debris. Get it? Is there an emoji for a groan, or let's come on the screen now? I don't know. Anyway, I'm here all night. So we've got a cheese moon, which we're going to assume is spherical. Okay, this is a moon made of cheese. Made of cheese. Okay, let's assume this has a constant density. Rho. Now, would anyone like to have a guess, or perhaps look up if you have the interweb with you? Can someone tell me what type of cheese we're going to use? There are lots of variants, okay, but I'd like the density from the cheese, please. So if you want to suggest a density, that would be lovely. We had some quite soft cheese in my class today, but maybe there's a harder cheese which we could use. Although, given it's probably going to be in the interstellar space, the cheese is going to be pretty hard anyway. What do we got? What do you reckon the density of cheese is?
There's 1,100 kilograms per meters cubed.
That's an excellent suggestion. Okay, that will give us a very nice answer. So if that's one who I was teaching today, thank you very much for that. Right, 1,100 kilograms per cubic meter. I think it's about cheddar, I think, something like this. Okay, it's ironic actually because I'm actually allergic to cheese. I can't eat it. So there we go. I'm doing this for your benefit. Let's call that radius R. All right. Now, one of you have decided to be an astronaut. Okay. I suppose we could call you Wallace and Gromit. Maybe this would be Gromit here, or perhaps Wallace on the cheese moon. And you're going to be leaping with velocity u from the cheese moon. And what you'd like to do is you'd like to escape the cheese moon. Okay. So a bit later, you could be going like this. As long as you have no sort of rocket boosters. All right, maybe that could be distance. Maybe that could be distance r away. Okay, what you'd like to do is escape the cheese moon, I think. All right, so let's work that out. So what do we got? We got forces on you. There's a force of gravity, which is your weight mg. Okay. In fact, let's write this. Let's just do that there. Rather than mg. Oops, I've just got rid of my cheese moon. There we go. Let's try that. So, right, and there'll be some sort of normal contact force, I guess, at this point. But let's just say you've just left. So let's just think about that on there. Actually, let's have the normal contact force just at that point. And at here you've got mg, but it's a bit further out. So that's g at r, and that's going to be g at little r. There's your weight. So the best way of thinking about this is in terms of energy. Now, for some of you, maybe this might be a new concept. The total energy, if we have assume no work is done by rocket boosters, etc. No work is done by rocket boosters, etc. Okay, let's check the time. So we've got the kinetic energy that we started with, half mu squared. This little person is of mass m. We then got the gravitational potential energy, which is minus gmm over r. Okay, so negative gravitational potential energy. What is this, you might ask? Well, if you think about it, I've got to do some work to get to zero. All right, if I've got to sort of do work against gravity. So if I'm a long way away from my planet, then I will have zero gravitational potential energy. So I'm in debt to start off with. So I've got to do work, positive work, to get to zero. So it'd be like having a negative number in your bank balance. All right, you add some money there and you might get to zero, and you never know, you might be positive. So that's the total energy. This is the GPE. It is generally a negative quantity, and this is my kinetic energy. So and a bit later on, of course, if we wanted to, we could work out the velocity So half mv squared minus gmm over little r. That'd be nice. Now, but we want to escape the cheese moon. So to escape the cheese moon, so basically you're jumping up and say, have you got enough kinetic energy to escape the cheese moon? Okay, then E must be bigger than 0. That means when we're really far away, we've still got some kinetic energy left. All right, so in other words, still some kinetic energy left when R tends to infinity. All right, which you can kind of see from this one. And of course, E is the constant. This means, so we have a constant E. Brilliant. Right, so therefore we can just use this one, this little equation here. So if E is bigger than 0, therefore we've got a half mu squared minus gmm over r is bigger than 0. Lovely. We can define what we call the escape velocity. And there's lots of nice problems like black holes, etc. We can go from there, but that's not what we want, because what sort of kinetic energy could we do? So let's go back on Earth and let's see how much kinetic energy we can use. So I did this little thing today with my 4th years, and I got them to, actually top years, apologies. So I got them to leap up and down, or at least up like this, and see how much kinetic energy they can gain. So we had about 0.45 meters, I think, something like that. Something like that. Okay, I think maybe 0.4 actually. Can't exactly remember the numbers we had. Okay, so there we go. So rather than having our kinetic energy, now if that was the mass m, imagine you've not lost any mass in going into space. All right. So what you can assume is that half mu squared, all right, is going to be, remember this is g on Earth, all right, is going to be mg Earth times h. Let's call that h. Right, so the masses cancel. So what we can do is I can replace half mu squared with the GPE gain. So let's just say we generate the same amount of kinetic energy. So that one can be mg on Earth times h. And of course we can measure that, so you can do that. So let's that means we can cancel the mass, which is rather nice. And so what we've got is we've got g Earth h is bigger than g big M over r. Now we've got the density of the cheese moon, so let's we don't know the radius of it, but we know the density. So let's go and figure this out. And basically what we want to do is we want to find out what the radius is, such that we can escape the cheese moon. So our mass is going to be 4/3 pi times r cubed times the density. So that means we've got g Earth h is bigger than big G times 4/3 pi r cubed rho over r. So we're going to cancel one of the r's. So if we put that all on one side, so what do we got? We've got g Earth times the height times 3. And then we've got 4g pi rho, and that's going to be bigger than r squared because we've got a cancelling r. And then lastly, let's put that in. So r is going to be less than, which makes sense, of 3g Earth h over 4g pi rho. Let's put in some numbers. So what have we got? We've got 3 times 9.8, 0.4. 4 times 6.67 times 10 to the minus 11 times pi and times rho, which is 1100, I think. I'm just going to stick that into my calculator. Let's see if I've got that right. So bear with me. This is where you can grab your calculators and see you can get the similar answer to it. It's 3 times 9.8 times 0.4. You hear me tapping my calculator in the background. There it is. Times 6.67 10 to the minus 11. Times shift pi and then times 100, and I make that 3571. Let's call it 3570 meters. So in other words, if my cheese moon is less than about 3.5 kilometers in radius, you'll be able to escape it. Okay, so so you can escape a cheese moon. Now some of you may be amazing athletes, so maybe you can escape a larger cheese moon, all right, if the radius is less than about 3.5 kilometers. Now we've got 5 minutes left, so a development of this will be, well, okay, We've assumed our cheese moon is spherical. Well, is that going to be true? Well, I think we need to think about whether our cheese moon is rotating or not. So this kind of leads to sort of quite some nice astrophysics, actually, about what happens when you rotate too fast. In fact, indeed, why things become spheres. Something called the potato radius, but that's not quite what we're going to solve at the moment. So in other words, if we have our rotating cheese moon, let's say it goes round with a period of T rot. Okay, and what we want to do is work out a kind of a upper limit of, or a low limit rather, for our rotational period. If it's less than a certain period, our cheese moon might fragment, and then it wouldn't be a cheese moon anymore. So what we're going to assume is we're going to have a little bit of cheese just on the boundary at the equator, and of course that little bit of cheese is going to be moving in a circle. Okay, that thing's rotating. Whereas you look at the top there, that little blob of cheese isn't. So let's have a look at the forces on this bit of cheese. Well, it's got its strength of gravity, so mg, so that little mass is little mass m. That's big M, which is 4/3 pi rho r cubed. Okay, and that's r there. And we've also got a normal contact force acting on that, which I'm going to call big R. Confusion possibility for that of also the radius here, so make sure that's a lowercase. Okay, so we've got the normal contact force, because if you're standing, you're not falling towards the center of the Earth. You've got a normal contact force offsetting your weight. So what's going to go on here? So let's go for Newton 2 radially inwards. Now what we've got, this is executing circular motion because it's rotating. So we've got mv squared on r. Now there's v, which is going towards, that's the velocity. If you're on the Earth, that's about 0.5 kilometer a second. So mv squared on r is going to be the weight, mg, minus our normal contact force. Now, this normal contact force kind of idea allows us to think about the limit of when our cheese moon would fragment. Because if our normal contact force becomes 0, then we've got a problem. So if we rearrange that, we've got r is going to be the weight minus mv squared on r, our centripetal force, if you like. That's what we call it. Sort of, it's not really a force. It is the mass times acceleration. But we rearrange it to make r the subject. It kind of seems like a fictitious force. All right. Okay. So what do we got? Let's put the things in. So we've got our g is going to be g times m. So g 4/3 pi rho r cubed over r squared, gm over r squared. Okay, that's our strength of gravity over our period t rot. So therefore v squared is going to be 4 pi squared r squared over t rot squared. Let's put that all together and then see what we've got. So therefore our normal contact force is going to be this lot. So 4/3 pi rho g times the mass. We've got r cubed over r, so that's an r. All right, and then we've got minus m times v squared, so m times 4 pi squared r squared over t rot squared. T rot squared. Have I got that right? I think I have. Have I got? I've got some. Hang on a minute. Anyway, that's hang on a minute. So not quite. It's v squared over r, isn't it? So mv squared divided by r, and that's, yes, I need an r there. I've got too many r's. There we are. There we are. So it's v squared over r. So if r is basically r must be bigger than 0 for the cheese moon not to fall apart. I'll finish this off. Not to fall apart. What this will mean is we can work out for, we can basically, and have you noticed that r cancels on this? So what have we got? Let's put this all together. So we've got the m's cancel. We've got a 4 pi cancels, leaving a pi. And so let's put this on one side. We've got r pi over t rot squared. All right, that's going to be bigger than 0. So anyway, let's just make sure I got my inequalities right. So we've got, what do we got? We've got rho g on 3 times r minus pi r on t rot squared must be bigger than 0. So there we go. So we can cancel the r's. This is rather nice, isn't it? So rho g on 3 is bigger than pi on t rot squared. Let's keep going. So we've got t rot squared, okay, is bigger than 3 pi on rho g. T rot is bigger than the square root of 3 pi on rho g. And that kind of fraction crops up in all sorts of cool places, including things involving general relativity. So we've got the rotational period involved just the density. So if we put that, what have we got? 3 pi. And I think we had 1100 times 6.67 times 10 to the minus 11. I think we get a nice number here. Let's just type it out. So square root. Okay, so 3 shift pi divided by 1100, oops, times 6.67 e to the minus 11. And I get 11333 seconds. If we divide that by 3,600, we get 3.1. It's not quite 3.14, I'm afraid. There's an 8 here. Hours. So that's approximately pi hours. Okay. So amazingly, because this is a pretty niche example, and thank you for, I've gone 1 minute over, but I hope you enjoy this. So if we have a moon made of cheese, I think it's got to be cheddar, 1100 kilograms per cubic meter, then if the rotational period of that cheese moon is bigger than pi hours, then the cheese moon remains a sphere. If it's less than that, it will start to cause debris. There we go. Anyway, lovely. Thank you very much, everybody. Next time, we will probably go to the back of the book, and I think we'll have a look at the last 2 questions, because that involves things like buoyancy, which you will meet in physics, but rarely you probably actually have to do a good question on it. So Archimedean upthrust. So it's questions S and T. Sorry, not S and T. So R and S are really good. And also next time, we'll have a look at something quite different, which probably will be one of the photons. So maybe something like I. Okay, and then we'll go from there. Thank you very much for coming along. Bring your friends. I will see you next time. Thank you very much. Okay, let's unshare that. Okay. Good evening. I would highly recommend not eating lots of cheese now, because you just won't sleep. All right, but there we go. Maybe tomorrow. Okay, I think we can probably. Should we stop the recording now?